Okay, so it's about time to start. We have several guests in our classroom today, and I told all of the people that emailed me, these are y'all are prospective students, right? And so I got quite a few more students who asked, hey, can we come visit your class? And I wrote back and said, I don't know, there might not be enough space. And it looks like those concerns were completely overblown. We have lots of space today. That's nice. Okay, so back into the material. Remember, there's a list of examples that I wanted to go through on the Chapter 15 material. So this is not specifically 15.7. This is Chapter 15 kind of, let's call it review in some sense. Along the lines of, how do you apply the many theorems that we've talked about? Strategically speaking, I want to compute line integrals and surface integrals. What's the most effective way to use our various tools to do that? So I'm going to show you how to implement this strategy, how to make the most use of our diagram that I have here, right? It's a little bit overwhelming to look at it once, right? But how is this a useful tool? So remember, figure out what have you been asked to compute and where is that in the diagram. That will then tell you which two of the big theorems have any possible chance of being useful. Don't bother thinking about the other ones. They couldn't possibly be useful. Okay? Do what the diagram tells you to do. The diagram will tell you, look, whatever your integrand is, there's a certain operator that you should compute by virtue of there being an arrow there saying, hey, compute this. And do it. Right? It's easy to do. And one way or the other, that information is very likely to be useful. So you'll have somewhere between 0 and 2, then boundary theorems, or I guess I've been more so calling them accumulation theorems this term. But anyway, those kinds of theorems, somewhere between 0 and 2 of them will be relevant. Don't forget to consider path independence and surface independence. Every so often you get lucky geometrically, more often than you would think, by the way. Again, reminder based on my own personal experience. And so you'll have a list of options, and just enumerate your options. Look at the problem, try to decide which ones are most likely to be useful, most likely to be the least amount of effort, and do whichever one looks the easiest. Okay, so we're going to do that. Here, let's start with this example. We are being asked to compute a line integral. A line integral in R2 or in R3? Well, this parametric curve has 3 coordinates. So this is clearly a curve in R3. Yeah? Okay, so over at our diagram, we're being asked to compute one of these. That means these are our 2 options. Gauss's theorem will have nothing to do with this question. The divergence of this vector field is absolutely irrelevant. Right? So don't waste your time with any of that. No triple integrals will all be part of what we're about to do. Okay. All right, so let's see. What does the diagram tell us to do? The diagram tells us that if you're looking for this line integral, it says compute the curl. Right? We were given a vector field. This is what we want to compute. So here's where we are. The diagram says compute the curl. So let's do that. Okay, now here's my little shortcut for computing curls. Remember, there's a formula, right? It's a symbolic determinant, and I like to just take the vector field as it's written here and put partial x, partial y, partial z, I, j, k, like that, and there's what I'm taking a determinant of. In fact, I don't even usually write this down. I just kind of remember that that's what's up there, and that tells you what partial derivatives to take. So specifically, if you want to compute this curl cross f, right? Well, this first coordinate is going to come from the y partial of that minus the z partial of that. And I don't really need all this stuff that I wrote down up here. I don't really need for that to physically be there on the page. I just need to remember, okay, yeah, that's what I'm doing. And so that y partial minus that z partial is 0. Okay, second coordinate. The second coordinate is going to be, well, I'm going to take the z partial of that minus the x partial of that. And let's see here, the z partial is 2x, the x partial is 2x. Okay, so again with the 0, how nice is that? Lucky break. Right? Fingers crossed. Come on, 0. All right, let's look at the third component. This third component is going to be the x partial of that minus the y partial of that, and sure enough, 0 minus 2. Let's see, 2y minus 2y, and that gives me 0. Okay, so you can compute curls pretty quickly. I mean, in practice, like I say, you don't really need to write this down. Just remember the structure, and then in your mind, you're like, okay, well, let's see that first component. I need to take that y partial minus that z partial. Okay, so there's my curl. What does that curl tell us? The fact that the curl is 0 tells me that there is an anti-gradient. Right, so fundamental theorem of line integrals is on the table. We could totally do that. And in fact, look, if you feel like, look, come on, that's easy enough. Well, do I really need to consider the possibility of options better than that? Because that's going to work out great, right? So if you want to just take that and run with it, I mean, you totally can. Let's consider the rest of our options, though. This curve here now. Can I use Stokes' curl theorem? If I were going to use Stokes' curl theorem, I would need for this curve to be a boundary. I would need to know that there is an anti-boundary. How am I going to decide if my curve is a boundary? Well, gosh, I mean, geometrically, that's kind of a hard problem until you realize that all boundary curves are closed curves, right? And if a curve is not a boundary curve, if a curve is not a closed curve, it can't be a boundary curve. That's a geometric appeal. Right? Okay. So is this a closed curve? Well, just take 0, plug it in, see what you get. Take 1, plug it in, see what you get, and compare. Are those the same point? Are they not the same point? And it's easy to see just by looking at that coordinate right there. They're clearly not the same point. They have different z coordinates at a glance. So this is not a closed curve. Therefore, this curve is not a boundary of a surface, and therefore, Stokes' curl theorem is not on the table. Everybody see how we're going about this? Okay. By the way, I suppose, here's another possibility. I mean, we did compute the curl. We did get 0. That means path independence is another option. So I could take this path here. I could take the starting point, take the ending point. I could recognize that while the curve does all sorts of wacky nonsense, I could say, you know what, I don't like that curve. I'm just going to take this curve instead. And that would also be fine, right? You could say, let's do that. You could reparameterize, and that's an option. But honestly, I feel like the fundamental theorem is going to be the easiest of my options at this point. Everybody on board? Finding the anti-gradient. You can just kind of eyeball that. The anti-gradient here, it's going to be a couple of anti-partials, and none of them look hard. So I think we've got it. I think we've got this diagnosed. Everybody happy? Time being a factor, I'm going to let you all finish the details on this on your own. Obviously, you can ask questions in office hours if you're not sure how to proceed from here. Okie dokie. Moving along. Here's another question. Got a vector field. This is clearly again an R3, looking at a line integral. So on our diagram, we are again here. Right? So this is what we're trying to compute. Here therefore are our two options. Again, we're going to compute the curl. By the way, this curl, you might even be able to compute in your head. Anybody want to compute that curl for me in your head? What do you get? Nobody? 0. Yeah, very good. Okay, let me show you why this is 0. we're taking various partial derivatives, right? I mean, but notice we're always taking kind of off partials. So we're taking the y partial of the z component, and we're taking the z partial of the y component. And so since there are only x's in here, the y partial is going to be 0, the z partial is going to be 0, because there's no y's and there's no z's. And likewise, we're going to take a couple of different derivatives of this, but it's going to be x partials and z partials. There are no x's, there are no z's. Right? So at a glance, this is a good thing to kind of be on the lookout for. If there's all x's there, and all y's there, and all z's there, curl is 0. Right? So, anyway, that's something to keep in mind, save you a little bit of time. So the curl is 0, and that means that we have the same two options that we had previously, namely, there is an anti-gradient, and I can use the fundamental theorem of calculus. Also, it's path independent. And so I could, take the endpoints and parameterize a straight line instead of this wacky thing. And that would be another option. Okay. There is, however, a third option here. Notice that when you plug in t equals 0 at the starting point, when you plug in t equals 1 at the ending point, you get the same point. So this curve, wacky though it is, starts and ends at the same point. And so now there's, occasionally there's, awkward geometry, and I suppose it's possible that a curve could tie itself in a knot or something, right? But it's not something you really need to worry about most of the time. And there's a bunch of details inside of what I just said there that's not Math 212 appropriate, but it's not really our problem. So we can act as if there is a surface here that this is the boundary of. So a third option then is to use Stokes' curl theorem. Right? Good news, we've already computed that curl. Right? Okay, so let me outline how both of these options work out then. Calculation wise, one option here is we could say I can compute the anti-gradient and say this line integral is let's see here, it would be f of b minus f of a. That's an option. Here's another option. I could say I'm computing the flux over the anti-boundary surface of the curl of that vector field. And either one of these would be a really convenient and perfectly fine way to answer this question. Both of these instantly tell you that the answer to this question is 0. So, why? Well, we already agreed that the starting and ending points are the same point, and so this is f of a minus f of a, which is obviously 0. Right? Also, we've already computed the curl of this vector field. The curl is 0, so we're doing a flux integral of 0, which is also 0. So, as to which argument you use, should you do like that, or should you do like that? I don't know. Suit yourself. Whichever one you like better. Yeah.
How would you find the normal vector of that boundary surface if the curl wasn't 0?
Oh, yeah. No, I haven't got the slightest. Yeah, no, that would be absolutely. That would be very, very hard, and I don't know. Yes.
What if the line doesn't tie itself? What if the curve?
What if the what?
What if the curve doesn't form a closed surface, but kind of go here and then go back again?
So that's one of these exceptional cases that we kind of don't need to worry about. As we're applying it here, it just ends up not mattering. Yeah, right. Okay, so this one works out very nicely. Why am I erasing that? That's not hurting anybody. Let's leave that there. Okay, third example. This is an interesting one. Let's compute the curl. Sorry, getting ahead of myself. Line integral, clearly in R3. Therefore, as usual, as previously, I should say, there's nothing usual about it, but as previously, here are our two options. We compute the curl as the diagram instructs. By the way, you notice how much I'm relying on the diagram? It's telling me my options, it's telling me what to do, and it's giving me a framework in which to do all the thinking that I'm doing about how to compute these questions. All right, so that's, again, I urge you, memorize this diagram. I know it looks like a lot, but the patterns are so extremely strong. Once you notice the patterns, it's not that much to memorize. It's really, really helpful to do that. Okay. Right, so going back up to here. Let's see, so compute the curl. Playing the usual game. Let's see, the first component. Y partial of that is 0, Z partial of that is 1. So the first component is 1. Then let's see here, the Z partial of that is 0, the X partial of that is 1. So, I'm sorry, I forgot my minus sign. So I get minus 1. And then last component, X partial of that is 0, Y partial of that is 1. So minus 1. So there's our curl. It's not 0. Not getting 0. That means that there is no anti-curl. Fundamental theorem of line integrals is not on the table. It makes no sense at all. If you were to write down, f of b minus f of a, that makes no sense. You're evaluating something that doesn't exist. It's not that we can't find it. It's not that current techniques. No, it doesn't exist if you're writing down garbage. Right, so don't go over here for this question because the curl was not 0. Okay, so our only remaining option, at least between these two theorems, is Stokes' theorem. So we ask, is there an anti-boundary? Is this curve a boundary of something? Okay, well, let's see here. What is our curve? Our curve, I'm going to have to draw a picture here, aren't I? We're looking at how this cylinder intersects with this plane. Oh, okay, so hard to draw. And I appeal to your geometric intuition. That intersection is it's a tilted ellipse like that. Everybody on board? Okay. All right. So is that tilt? Oh, wait a second. Oriented counterclockwise as seen from above. Okay. So as if we were to look from up there, oriented counterclockwise, and so that means that the orientation is like this. All right. And that first one didn't come out very well. There we go. So there's our orientation. So is this a boundary of some surface? Well, yes, it is. This is a closed curve. It wasn't given parametrized, right? But it is a closed curve. So this is a boundary, and it's a boundary of a lot of different surfaces. By the way, clever laziness suggests we should pick that part of. By the way, that part of this plane. Right, so that's not just any old plane. We know what plane that is. Okay, so we could rewrite this as a flux. We could rewrite this using Stokes' curl theorem. Let's see here. I'll use orange. This integral is flux through this new surface, I'll call S, of the curl dot ds. And here's where we have to kind of face up to, okay, how useful was this? Is this something that's convenient? How would I find my ds vector? Well, let's see here. I could parameterize and do in du dv, right? My surface is a graph, right? Solve for z, no big deal. Solve for z, get a function of x and y, use the graph parameterization. Compute the partial with respect to u, the partial with respect to v. Take the cross. It's a whole game, right? It's a whole 15.5 plug and chug. But you could do that, and that's fine. And then you think to yourself, well, maybe how about this? Why don't I just write down instead of that, I can see this vector from the equation of the plane, or so it seems. Right? Isn't my normal vector necessarily 1, 1, 1? That is not valid reasoning. This is a dangerous little landmine that lots of students step on. One thing you have to remember is, back in chapter 12, when we were talking about, the coefficients in the equation of the plane give you a normal vector. Well, it is a normal vector, but it's just a normal vector. There is nothing special about it. You cannot assume that just because, the equation of the plane happened to be written in that form, that is exactly the right capital N. Remember, this capital N in here, this is not just any old vector. That has to come from the parameterization. Right? The magnitude of that capital N vector means something. The magnitude of that capital N vector means what is the stretching factor. That stretching factor is why you can rewrite this as du dv. It's very important what that magnitude is. And if you just pick a random normal vector, it doesn't work. You might get lucky. I suppose it's possible you get lucky. But it's certainly not valid reasoning. Is everybody on board? Does everybody see what I'm talking about? So be careful not to step on this landmine, like I say, because it seems like it would be a valid argument, but it isn't. Okay. All right. So here's another thing you could do. You could say, all right, well, foo on that. Why don't I instead write this as little n unit vector times d capital S, and you can do that, and you can write down what this little n is. It's it's 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. That's clearly the unit vector there, and that's fine, true. And now look, you've got arithmetic to compute that dot product. Isn't it all smooth sailing from here? Well, okay, now the problem is, you still have to compute this integral. You still need to know what that d capital S is. It's a surface integral. It's an area, right? But this is an area of a tilted ellipse, and I don't know the formula for that. How do I compute that area? Well, you would parameterize and compute the magnitude of capital N, right? So this buys you nothing in this case. And you'd still have to go through that whole capital N process. Everybody on board? Good news, it's not that bad, right? The whole capital N thing, you take a couple of partial derivatives of your parameterization. You do a cross product. Everything in sight's a constant here. It's really pretty straightforward. So go ahead and just do that. That'd be my suggestion. Okay, here's the last observation I'll make about this example. Looking back at the original question, I'm just going to have to erase because this is kind of in my way now. The last observation. There is another way to compute this that we have not previously discussed. And that is, you could just directly plug and chug, right? You can parameterize this curve. It's not hard to parameterize. X and Y are sine theta and cosine, or let's say sine t and cosine t. Once you know X and Y, Z is easy to compute. You could just parameterize it. The vector field's really easy. All you would end up with is a couple of trig integrals, and it's not 100% clear which is going to be the easier way to do it. The parameterize and pullback on the curve itself, pretty doable. Right? The resulting flux calculation, if you make a Stokes' theorem argument, it's pretty doable. You get to decide which one you like best. One thing I would encourage y'all to do is go ahead and do both for this question, right? Crank them out, right? All the details and everything. For one thing, make sure you get the same answer both ways, right? That you certainly should. For another thing, you'll then have a clear picture of what the comparison is between those two options. and that'll help you make decisions about this kind of thing when time matters, namely on the exams. Okay. All right. Now here's a very similar looking question. It's the same vector field. It's the same cylinder. The only difference here, I'm intersecting with a different plane. And the reason I'm showing you this very, very, very similar question is just to point out that the devil's in the details. And so sometimes these little details matter. In this case, quick picture. Whoa, forgot to switch to pencil mode. In this case, we've got our cylinder. We've got our plane. It's a different plane, so let me respect that. So we're now looking at a different tilted ellipse. And again, you can parameterize. Again, you can do Stokes' theorem. Okay. This is also one of those situations where sometimes you get geometric good fortune. So, whoops. Come on. This surface here, I can easily write down the normal vector. That normal vector is again looking from there. Don't make the mistake of writing 1, 0, negative 1 over the square root of 3. That normal vector is pointing the wrong way. Think about orientations. Got to be careful with there's so many little moving parts here. Oriented counterclockwise from above. Think about what that means, and our normal vector should be pointing up. Don't make your normal vector point down if it points up. Yep. Yes, thank you. Yeah, good catch. Absolutely. Yeah. So this should be negative 1, 0, 1. Another way to say that little lesson is don't put too much stock in how this equation was written, right? This equation, x minus y equals 0, is totally equivalent and no better than the equation, that's supposed to be a z. Totally equivalent and no better than the equation z minus x equals 0, which likewise totally equivalent and no better than the equation 5z minus 5x equals 0. Right? So this idea that somehow there's significance in meaning. Look at the coefficients, and the coefficients are going to tell you something really important. Not really. Right? Certainly not up to scalar. The scalar, the magnitude of the resulting normal vector that you just peel off of the equation is meaningless. Okay. All right. Okay. Yeah. So here's what's nice though. Let's write down the resulting flux. Our flux is flux through this surface S of curl cross that normal vector d capital S, and in a bit of good fortune, that dot product is 0, and we are done with that question, right? So don't have to parameterize after all in this case. Like I say, every so often you get lucky, more often than you would think. So always heads up, always be on the lookout for this kind of freebie. Okay, here's a great one. This is one of my favorite of these examples. Let's see now. Where are we on the diagram? We're being asked to compute a flux in R3. So now our options have changed, right? We're computing one of these. So these are our options. So anything vaguely resembling the fundamental theorem of line integrals has got nothing to do with this question, right? So again, that's a bad look. If your solution has f of b minus f of a written on it on a question that has asked for flux, doesn't look good, right? So likewise, I don't want to see anything about antigradients on a question like this. Okay. So these are our two options. What does the diagram tell us to do? It says compute the divergence. That's what it says. So let's follow the instructions. Anybody compute? Well, this one actually you probably can compute in your head, but I claim even without doing any calculations, you should immediately know what the divergence of this vector field is. Note the hint. this is a curl field, and the divergence of a curl field is always 0. Right? Back to the diagram. We are given that the vector field I'm interested in is the curl of a given vector field, and therefore the divergence must be 0. That's that little theorem down there. Okay, so sweet. Not only is there an anti-curl, but we know what the anti-curl is. I see the anti-curl. The anti-curl is given. So that means that Stokes' curl theorem is on the table. And that's the actual possibility. I could rewrite this question as a line integral. Let's consider our other options. What about Gauss's divergence theorem? Is our surface, we need to know now, is this surface here, is that surface a boundary of a solid? Well, let's look back at it. Is this surface the boundary of a solid? Okay, we've got a paraboloid. Let's draw a... Here. This is an upside down paraboloid. We're looking at the part where z is greater than or equal to 0. So that's what we're actually interested in. There's our surface right there. Is this a boundary of something? Be very, very careful. Again, it's tempting. It's tempting to think, oh yeah, it's a boundary because look, I drew this circle here as the edge, and therefore don't I just get to fill that in for free or something? Absolutely not. Right? These points here do not satisfy that equation. The surface requires that your points satisfy both of these requirements. This is an intersection. Right? So there is no bottom face down here. This is just an upside down cereal bowl. And it is not a boundary. It's open at the bottom. Everybody on board? Be real careful with that. Okay, so it would be completely wrong to say, oh, it's a boundary of a solid, and therefore, yeah, I'm going to use Gauss's divergence. Like if you were to turn this flux integral into a triple integral, it's got no basis in the real what this question's really about, right? So that's not worth any points. If you say triple integral of the divergence, oh, hey, by the way, look how tempting that is. The divergence is 0. Oh, you see daylight, right? You're like, oh, it's a triple integral. The divergence is 0. The triple integral of 0, that's 0. I'm done. Boom, turn the page, right? So want to do that. Totally wrong. Okay, so can't use that theorem. All right, so should you just proceed with Stokes' curl theorem? Again, slow down. Don't forget. Consider, always be on the lookout for geometric good fortune, path independence, surface independence. And in this case, because we know that the divergence is 0, we've already computed the divergence, we got 0, we know that surface independence applies. Right? So that's our other option. We could just do surface independence. So which should you do? Again, it's kind of your option. The first option to do Stokes' curl theorem would be to rewrite this as a line integral over the boundary curve of the anti-curl. There's the anti-curl. Dot dx. Right? So there's your first option. And it turns out this is a great option. This is a really good way to do it. Because, again, let's look at our picture. Our surface was this upside down cereal bowl. This boundary curve here, the boundary curve C, is entirely contained in the xy plane, and so our dx vector is always entirely horizontal. Right? So I could rewrite this dx vector, for example, as dx scalar, dy scalar, 0. And look how nice that dot product is. So this is a great option. Stokes' curl theorem is very, very cool here. Everybody on board? You could also just parameterize that curve. It's just a ellipse. Oh no, excuse me. It's an ellipse. It's not that hard to parameterize that ellipse. And if you do parameterize that ellipse, when you write down x prime as part of x prime dt, you'll find that x prime has a 0 here. Okay. Here's the other option, though. The surface independence option is to say, this surface that I'm given, Fooey on that surface is curved. I don't like curved. I have a strong preference instead for this surface down here that has the same boundary. Right, that surface would be much better. Let's call this E, because it's the solid ellipse. Flux through E of f dot ds. Our vector field dot ds. What is our ds? Let's see here. Our ds on this new surface points straight up and is therefore 0, 0 ds scalar. And again, the dot product is kind of awesome, right? So pick your favorite. You can make a surface independence argument like I have on the right. You can make a Stokes' theorem argument like I have on the left. Either way, it's going to work out fantastic. Everybody good? And the divergence theorem is a landmine because this surface is not a boundary. Yes? Oh yeah, so the ds vector, keep in mind, is it's a vector. There's different ways to write it, right? I mean, so you can think of it as little n ds scalar, right here. Little n ds scalar, and this little n here is clearly 0, 0, 1. So that'd be one way to do it. Yeah, and so in fact, maybe it'd be a little bit more aesthetically appealing or familiar if I were to write it like that. Yeah. Well, the fact that z is greater than or equal to 0, this is what means that sort of cutoff edge is in this plane, and then that plane, being as it is entirely horizontal, is why its normal vector is entirely vertical. Yeah, right. Okay. All right, this last example is a nice and quick one. We have here a vector field, a little bit of quick algebra. It's not hard to persuade yourself that the curl is not 0. Right? I'm getting ahead of myself on the diagram here. Looking at a flux, these are our options. We compute the curl, and it's not 0. That means there is no anti-curl. Stokes' curl theorem does not apply. No line integrals are relevant in solving of this problem. Right? So steer clear of all of this for this application.
Yeah. You mean the divergence is not 0?
Yeah, the divergence is not 0.
Okay.
And that means that there is no anti-curl. Stokes' curl theorem doesn't apply, and line integrals don't have anything to do with, it's entirely possible I misspoke. If I did, I apologize. Yeah. Okay. So, can I use Gauss's divergence theorem? Well, again, as always, I would need for my surface to be a boundary of a solid. Is that the case here? Is my surface a boundary of a solid? No, my surface is the unit sphere oriented outward. Is that a boundary? Well, yes, it is. And how nice is that, right? So this is a boundary. It's a boundary of this ball, right? And so I can rewrite this as a triple integral over the ball of the divergence of this vector field. And that divergence is pretty easy to compute, and you end up with a triple integral That's not bad to compute. In fact, very easy to compute. Let me just check there. Details again for y'all to fill in later. So again, my goal here is to diagnose and strategize the details we've already covered. Everybody happy? Okay. So moving along, we now have 9 minutes to talk about optimization. Good news, I have a lot more pages here on optimization than I have really need to cover them. A lot of this is just kind of perspective and supplemental ways of thinking about it that we don't really need. So I'm going to go, in fact, really fast. It's going to seem through these pages because the ideas are pretty straightforward. First, a flashback to Calc 1, right? You remember Calc 1 optimization. You have to check the interior. We have this whole process for how to check the interior, but then you always have to check your endpoints, right? That's one of the rules, a different way of saying it, but once you're done with all your interior work, don't forget to check your endpoints. Okay. So those endpoints are the boundary of this domain interval. Okay, so we're going to find ourselves in an analogous situation when we're doing multivariable optimization. When we're looking at by the way, the function we're trying to optimize is some real valued function, f, that's defined on a multivariable domain. That's why we call it multivariable optimization. We are still, though, optimizing. We are therefore looking for the biggest value. We are comparing outputs, bigger is smaller, and of course, bigger and smaller means real valued. So again, we find ourselves with an interior and a boundary. The boundary is different here. Now the boundary is not just 2 points. If someone were to say, oh yeah, don't forget to check the boundary, like it's just 2 points. You'd be like, there are infinitely many points on that boundary. How am I supposed to, I don't know how to do that. Right? So that's a very serious concern, and this boundary is going to be the subject of much discussion on next Wednesday, last day of class, right? That's constrained optimization. It's a big deal. It's a non-trivial discussion. So we're not going to worry about that right now. Right now, we're just going to worry about interiors. How do you find critical points in the interiors? Don't forget how the process worked for Calc 1. The big idea was, if you have a point like this one, or this one, where the function's differentiable and the derivative is not zero, something really simple happens, right? If the function's differentiable and the derivative is not zero, I can't be at the maximum because the function's in the process of increasing, right? I mean, am I at the top of the mountain if as I walk that way, I'm going uphill? Well, of course not. If you're still going uphill, you're not at the top of the mountain. It's an immediate kind of thing, right? And likewise, for this point over here, this point, now the derivative is negative, but that means that as you go that way, the function is increasing. If the function is still in the process of actively increasing, you're not at the maximum. Okay, so this is a process of elimination. When you do these calculations here, when you look for where the function is not differentiable, where you look for, take the derivative, set it equal to 0, what you're doing is you're looking for instances in which these assumptions fail, and I can therefore not eliminate the point as a possible maximum. You're not really finding a maximum. You're finding a point where your argument fails. Right? This is a big point about optimization. It's a process of elimination. You eliminate most of the points by way of this argument, but sometimes you just can't eliminate it because the argument doesn't work. And so you're left with these points that you can't eliminate. And it doesn't really mean much. Okay. Certainly it does not mean that you have a maximum, right? There's easy counterexamples. For one thing, it could be a minimum. Right? But worse, it could be that because the function's not differentiable, you just have some weird corner and it's neither a max nor a min. Or it could be that, your derivative's 0, but you're not at a max and you're not at a min either one. You're at a kind of a, I don't know what you'd call that, a shoulder point or something. An inflection point, I know is the term. But don't overinterpret from what happens when you take the derivative and set it equal to 0. Okay. All right. It does remain, though, and the big deal is if this happens, if the function's differentiable and the derivative is not 0, our function is actively increasing, and therefore that's definitely not a maximum, right? And the same thing works in multivariable. Note the deliberately similar layout. If at a certain point, if the function is differentiable and the gradient is non-zero, well, then that means the function is actively increasing as you go in the direction of that non-zero gradient. Right? That's what the gradient is. It's telling you what direction is the function increasing and how fast. If it's non-zero, the function is literally increasing, and again, therefore, not a max. So we end up with analogous reasoning process of how to find critical points. A critical point is where I can't eliminate it as a possibility, which happens if either of these conditions fails. Namely, we're looking for points where the function fails to be differentiable, or, to say it in a silly way, we're looking at points where the gradient fails to be non-zero. In other words, where it's equal to 0. Okay, so this is how you find maxes. Now, again, we're not saying that any such results will be. They could be minima, or they could be maxima. Sure, those are possibilities. They could be what they call saddle points, which I think totally is outdated terminology. I think everyone can agree we should call these Pringle points. Right? Who rides horses these days? Everybody eat Pringles. Then there's stuff like this. I mean, what do you call that? There is no single variable analog to this exactly. It's kind of a maximum in this sense. It's the biggest point, it's what you might call concave down in every direction as you're looking at cross sections that way, but it's an inflection point as you look in another direction. That's just weird, right? Multivariable optimization is full of all kinds of odd, anomalous things that simply do not exist in single variable. And one of my favorite examples is what they call the monkey saddle. So it's a saddle in the sense that you can see the monkey, he's got a spot for his leg to go down and a spot for his other leg, but he's also got a little spot for his tail to go down. So monkey saddle, right? Isn't that funny? And notice, and here's a sort of a clearer picture of it. You can see that this is fundamentally different from a regular saddle. It's got kind of 3 kind of upslope directions and 3 downslope directions, as opposed to a Pringle, which has 2 and 2. It's different. And then I'm endlessly amused at the fact that they actually put a monkey on a saddle on a dog. Isn't that funny? That's hilarious. Anyway, okay. So let's do one. Here's an application. Let's look at this function. Note this is a function defined on R2. We want to find the critical points. How do you find critical points? Step 1, where does this function fail to be differentiable? If that function fails to be differentiable anywhere, that's a critical point. All bets are off. I can't eliminate that as a possible maximum. Who knows? I'll have to figure something else out to analyze what's going on with that. But if I can find any points where the function fails to be differentiable, good news. This is a polynomial. Polynomials are differentiable everywhere. There is no failure of differentiability. So we don't get any critical points there. Next part of the question, where is the gradient 0? Where does the function fail to have non-zero gradient? Okay, well, so we're back to the old familiar thing from Calc 1, right? Take the kind of, if you will, derivative and set it equal to 0. Very familiar. And in this case, no big deal. Here's your gradient. You set it equal to 0. That leaves you, with 2 equations. This one, tells you x is 1 or negative 1. But I also know that this has to be true as well, and that immediately tells you y has got to be 0. So independent of what x is, y is definitely 0. And so therefore these are our 2 critical points. Yep?
If the negative 3 was the derivative of y, would it be 2y minus 3?
If what now?
Like if it's x cubed minus 3x plus y squared, y cubed lumped the negative 3 with the x. Like, would that be different if it was like...
Well, so what I have here, this is the x partial of that. So partial with respect to x. So, I mean, it's just what the x partial is. Does that make sense?
Yeah.
Yeah. Okay. Yep. Okay. Okay, so we are actually mostly done with what I need to. There's one more example that I need to do. Oh, and then there's that. Okay, so anyway, we'll pick up here on Wednesday, and I think I've already sent out email about the fair game material for Monday's exam. Did I already send out that email? Did I? No? Okay, I owe y'all an email. Anyway, it's going to be through the end of chapter 15. None of the chapter 13 material is going to be fair game for the midterm. Yeah.
Is it just like 14.8?
I believe so. I have to look back and see what was in my previous fair game thing. But I think you're right. Yeah. Don't forget to turn in your homework.